I'm not going to introduce any new concepts in this video. I'm simply building up my reservoir of model testing cases. I'm still testing two models for repeatable independent experiments. The zero hypothesis, model 1, has a fixed known success probability p, while the alternative hypothesis, model 2, has an unknown success rate. In the first case, I'm going to see if a particular survey done here on YouTube had a gender bias. In the second case, I'm rolling one of these two dice. One of them is loaded and one of them isn't. And I want to find out whether I'm rolling the loaded dice simply by studying the outcomes. Since the theme of the surrounding videos are models where the zero hypothesis turns out to be too simple, you get no prize for guessing whether I'm using the loaded die or not. Just as in the first hypothesis testing video, I'm looking at the binomial distribution and ask if a particular value for the success rate p is valid or not. So that will be a model with zero parameters, and the alternative will be the free binomial distribution described in clip 19, where the success rate p is a free parameter. First, we're going to take a look at the YouTube Religious Identity Survey. That was an online survey performed by the users snowfeet and websnarf in order to check for dependencies between various factors. Now, in a normal populace, there is approximately as many females as males. So a fair sample of the populace would be binomially distributed with probability p equal to 50% for being a female. And yes, I'm going to label females as success and males as failure. There'll be fewer protests that way, I think. Now the data was like this. There were 75 females in the survey of a total of 358 people. You don't need any statistics to start wondering about the prospect of this being a fair sample. With less than 21% being female, it certainly doesn't look like it. But if there were only 5 answers and one was female, we wouldn't be that suspicious, so there's more to it than just percentages. The two models are described here. M1 is that p equal to 0.5, while M2 is that p is free and has a prior distribution which is flat, meaning that anything goes. In order to check which way the wind blows, we can give those two models an equal prior probability. But we could also study the base factor instead, the likelihood of the data under model 1 divided by the likelihood under model 2. If we got that factor and the prior model probabilities, we can calculate the posterior model probabilities using base formula. And the base factor is easy to interpret. A base factor larger than 1 is evidence for model 1, and a base factor less than 1 is evidence for model 2. The larger above 1 the base factor is, the more will the probability for model 1 increase, and the more below 1 it is, the more will the probability for model 2 increase. If the prior model probabilities are equal, the relationship between the posterior model probabilities and the base factor becomes particularly easy. In order to calculate the base factor, we need the data likelihoods under the two models. The probability of the data under model 1 is fairly simple to calculate. We've got the expression for the binomial distribution from clip 17, and we've got the value for p. The data is k equal to 75 out of n equal to 358 trials. So that's just a matter of using a calculator. The answer is a likelihood of 5.6 times 10 to the power of minus 30. A pretty low probability, but that doesn't matter much until we get the probability under model 2. Now I've done the same trick as in the previous clip by dividing the free binomial model into a finite set of possible values of p. I'm putting each hundredth of a percent as a possibility. I've got a nice mathematical tool for dealing with that many possibilities, so that's not a problem. The prior probability of p is flat. The probability of the data under model 2 is the sum of the data likelihoods under each possible value of p times the prior probability of p. This sum turns out to be 0.28%, which is an enormous likelihood compared to that from model 1. the base factor becomes 2.0 times 10 to the power minus 27, which is another way of saying that the outcome was enormously more probable under Model 2 than under Model 1. This can also be seen from this graph, showing the predictive distribution of outcomes under the two models. Clearly, the outcome k equal to 75 is much more probable under Model 2 than under Model 1. If we plug the base factor into base formula with equal prior model probabilities, we get that the posterior probability for Model 1 is 2.0 times 10 to the power minus 27. So the zero hypothesis about a non-skewed sampling of males and females can be soundly rejected. The survey must have had a component that attracted the attention of males more than females. As it turned out, most of those answering the survey were also atheists, and it seems like males are more prone to identify themselves as that than females. So that's at least one possible explanation for the skew we found. Mind you, the point of the survey wasn't to check the rate of males and females in different religious groups, but rather to find whether there were dependencies, which there were clear evidence for. The second example is to check if a die is loaded. I'm rolling the die 100 times and simply report whether or not the outcome was a 6 or not. As I explained in clip 7 before rolling the die, it's no great reason to expect a 6 if the die is loaded or not. Well, unless you introduce knowledge about what kind of outcome is in demand, at least. So I'm using a maximum entropy prior for P under Model 2, which adjusts the free binomial distribution of the parameter P so that the prior success probability is 1 over 6. This kind of prior hasn't been discussed in much detail, but if I want to stay true to the principles in clip 7, I need to use it. However, if you just use the flat prior for P, you would get pretty much the same result. After rolling the die 100 times, I got a total of 66s, so you may well guess in which direction this is going. But let's do it anyhow. Model 1 gives a probability of 1.9 times 10 to the power minus 22 for this, while Model 2 gives a probability of 0.18%, meaning that the base factor is 1.1 times 10 to the power minus 19, and that with equal prior probability for the models, the posterior probability for this being the fair die is 1.1 times 10 to the power minus 19. This can again be illustrated with a graph of the predictive distribution of the two models. Model 2 can be seen to predict the outcome k equal to 60 with much greater probability than Model 1. So we can be almost certain that this is the loaded die, and indeed it is. Just as in the previous clip, Model 1 and Model 2 started with predicting the same success rate, but while Model 1 stayed the same, Model 2 became adjusted to the incoming data. That adjustment provided better predictions for the next data than Model 1, which is why Model 2 won in the game of probability against the zero hypothesis, Model 1. There really was a point in giving a finite probability for different values of the success rates in this case. But as in the previous clip, this was because we got a result that could be better described by Model 2 than Model 1. However, if Model 2 gave larger probabilities for some outcomes than Model 1, then it must have smaller probabilities for other possible outcomes, since the probabilities over the distinct possible outcomes must sum to 1. So what I'm preparing you for here is the concept that if we had chosen the other die, Model 1 would probably have won. And you can see that in this graph over the prior outcome probabilities for the two models. Just as for the same graph in the previous clip, there's a region here where Model 1 predicts better than Model 2. I happen to get an outcome outside that region, though, because I was using a loaded die. For the reasons explained in clip 18, I could pretty much trust getting such an evidence for the die being loaded when actually using such a die. With Model 2 getting wiser about the success rate in such a case, and with that rate different from 1/6, I could fairly reliably get evidence for this with enough data. Which is exactly what happened.